Okay, my name is Sally, and today I'll be talking about the synthesis of alcohols from ketones and aldehydes. So I'm just going to start with a brief overview of why ketones and aldehydes are so versatile and why they're so useful for different syntheses. To start that out, I'm going to talk about the oxidation state of both of these compounds, and then in turn why that leads to their versatility. So starting over here on the left, we have a ketone, which consists of a carbon double bonded to an oxygen. And that same carbon is also bonded to two different R groups, which can just be basically anything which is bonded to a carbon. And then over here on the right, we have an aldehyde, which is another carbon bonded to an R group and a hydrogen, and then that same double bond to an oxygen. So starting with the ketone, I'm going to draw down here to kind of represent what I'm talking about. So as you can tell, we have that oxygen, which is double bonded to a carbon. And so when we're determining an oxidation state, what we're really looking at is the number of electrons that are pulled away from and added to the particular atom that we're looking at. So when we're talking about the central carbon to this molecule, or functional group, because it's not a full molecule, but when we're looking at that, we can see that the oxygen double bonded to that carbon. Oxygen is an electronegative atom, so we know that the oxygen with those two double bonds is pulling those 4 electrons towards itself. And then we know that that carbon has those 2 other bonds to those different R groups. So then to find the oxidation state, we're going to take those 4 from the carbon, or from the oxygen, minus the 2 on the carbon, which will give us an overall oxidation state of +2. And then moving on to aldehydes, we can see over here that we have a similar situation. We'll start with that oxygen again. We have those 4 electrons that are being pulled away from that carbon by the oxygen. And then we also have on the carbon, this time we have 3, because that hydrogen is also an electron withdrawing group. So we'll take that 4 from the oxygen minus 3, which gives us an overall oxidation state of +1. And I just want to make sure it's clear that when I'm saying that, I'm talking about this central carbon has an oxidation state of +1. And same over here. It's the central carbon, which is +2. It's a bad plus. Okay, so now I want to talk about why oxidation state is important. So as we know, oxidation reactions involve the addition of oxygen, and reduction reactions are the addition of hydrogens. So there's kind of a scale of oxidation numbers from -4 all the way to +4. And so if something has an oxidation state below 4, it can still be oxidized. And if something has an oxidation state above -4, it can still be reduced. So if we look over here at the ketone, we're like right in the middle, we're in between. So that means that ketones can always be either oxidized or reduced. So they'll undergo both oxidation and reduction reactions. And it's the same thing with aldehydes, because that central carbon has that oxidation state of +1. So it can go both ways. They can be both oxidized and reduced. So that is particularly relevant because the reduction of both of these types of functional groups results in the creation of an alcohol. So that's what we'll go through next. The first important reduction reaction works for both aldehydes and ketones. For the sake of this example, I am going to write up the mechanism with an aldehyde. So I'll just start drawing here, but the important aspect of this particular reduction is the reagent sodium borohydride, which is NaBH4. This is a bit of a rough drawing, but essentially, the boron is negatively charged and it is kind of commuted with this positively charged sodium. And then over here we have our aldehyde. Okay, so the first step of this type of reduction is the addition step. So what we're going to see over here, I'm going to draw the arrows in a different color so it's easier to see. But this hydrogen from NaBH4 is going to do kind of a backside attack on that aldehyde, which is going to kick off the electrons from the double bond to that oxygen. And that's going to leave us with this over here. With this extra hydrogen coming off of that first carbon and a single bond to our oxygen up here. And I hope you can see those lone pairs. I know they're a little bit faint. All right, so now our oxygen is negatively charged and we have this guy in solution. So what's going to happen here is that our negatively charged oxygen, and this is going from the lone pairs, it's going to attack this hydrogen here, which is going to kick those electrons onto the oxygen. And we also, at this point, have BH3 in solution because we lost that hydrogen to our aldehyde. Okay, and this is a pretty simple reaction because we only have one more step. So this right here is the addition step where we're adding that extra hydrogen to the oxygen. And then our last step is protonation. So I'm just going to draw for a second here. Which I think I may have explained that a little bit badly. So this first step over here is addition, where we're adding that hydrogen to the aldehyde and breaking that double bond. And this second step here is the protonation, where we're adding that hydrogen proton to the oxygen. And so then over here is our final alcohol product. And that's supposed to be an H. But as you can see, that's a tertiary alcohol that's formed. And then over here in solution, we have our NaOH. And this is our first reduction, which, as I mentioned, is using sodium borohydride. Now you can do basically the same reaction using lithium aluminum hydride, which looks like this. And lithium aluminum hydride is a much more powerful reagent. And so with that one, you can perform the same reaction under very mild conditions. But I'm pretty sure lithium is more expensive. So that's why NaBH4 is typically used. All right. Okay, so I am going to go ahead and show a mechanism for the lithium aluminum hydride reagent because it is very widely applicable for this particular synthesis. So we'll start with this compound here, which is an aldehyde again, but again, this also works for ketones. And I'll just draw the basic reaction and then I'll go into the mechanism. So again, that's a lithium. It's lithium aluminum hydride. And then we also have THF. And like I mentioned, this can be performed at low temperatures because lithium aluminum hydride is such a strong reagent. So we can do that at low temperatures. I'm just going to write LT. And then it'll be an acidic workup at the end. So we got our H3O plus. And similar to the last reaction, this results in the production of an alcohol. Okay, so for the mechanism of this one, it's important to note at the beginning, and this is actually the same for the sodium borohydride. I neglected to mention that, but it requires 4 equivalents of the starting material to produce the product. And I'll show you why as we move into this mechanism. So we start out with our addition, or like you could also say like the association step, which is where the reagent and the lithium in particular associates with that oxygen on the starting material. So that I'm going to represent with this dotted line here. And that's because oxygen has those 2 lone pairs and lithium is very positively charged and a strong nucleophile. All right, and then I'll show our aluminum hydride here. This is tricky because I don't have an iPad. Okay, you'll just have to bear with me and believe me when I say that's aluminum hydride. And then I'll use a different color for arrows again, just so it's easy to see. So we are attacking that carbon again of the aldehyde in kind of a backside manner, which again kicks electrons onto that oxygen. And that just results in a breaking of the double bond and therefore a negative charge on our oxygen there. But also the addition of that hydrogen from the aluminum hydride down in the same place as it was with the sodium borohydride. So now we have our negatively charged oxygen up here with 6 lone pairs, or I guess 3 lone pairs, 6 electrons. And that's kind of loosely associated with the aluminum hydride. I'm not entirely sure how to represent that, but I'll do it with an arrow. Okay. So now we have, so like I mentioned at the beginning, you have to have 4 equivalents to proceed with this reaction. So from here on, I'm going to show 3 arrows to represent that you have to do this 3 times to end up with the final product. So this next compound is a little bit crazy looking, but essentially the same thing happens 4 times with these different equivalents, and it results in this gigantic compound. So what is really happening here is that the oxygen is associating with the aluminum, and that happens 4 times. So we have the aluminum in the center, and then our oxygen, which is bonded to essentially the starting material. And that is a cyclohexane. You just can't tell from my drawing. Okay. And then there should be an oxygen here. So let me erase it. All right, and then we have a last one here. Okay. So then at the end of this whole thing, once we have this gigantic compound, we're going to do that acidic workup with H3O plus. And that results in the dissociation of each of those kind of, I don't want to say individual compounds, but each of the remnants of the starting material that is associated with aluminum, those dissociate, and you still have that oxygen. And then with the acidic workup, we're protonating that oxygen, which leaves us with 4, that's an H, by the way. But that leaves us with 4 equivalents of that final alcohol. And in this case, you can see that that's a primary alcohol. But yeah, that's it for that reaction. Okay, so to briefly wrap up here, I think I'm getting close on time, but there are a couple other reagents that can do the same thing. So the other one that we talked about in class is called the Rainy nickel reagent. And this one is special because it has like it's very stable, and it also has extremely high catalytic activity at room temperature, which is good because then you can perform the reaction under pretty mild conditions. And yeah, so that one will do the same thing, and it can synthesize an alcohol from both a ketone and an aldehyde.